Take a look at this pole that's being stuck into a river. The pole isn't broken, it just looks that way. The rays of light coming off the pole are actually bending when they pass between the water and the air. Ever wonder what's going on here? Well, this phenomenon can be explained with Fermat's principle, which says that light travels between points along a path taking the least amount of time. In this lesson, we'll explore Fermat's principle and see if we can explain why light bends between water and air. So first off, suppose you have a ray of light that's traveling from this point down here to the point up here. According to Fermat's principle, light will follow a path that takes the least amount of time. So what path is that? Well, let's try drawing out a path like this. Down here, you can see how much time your path takes. So this is definitely not the path taking the least time. See if you can find the fastest path, one that's faster than the goal time down here. Exactly, so the fastest path between these 2 points is a straight line. That's why you'll often hear that rays of light travel in straight lines, because that's usually the quickest path. So then why does light bend sometimes? Well, now let's look at the case where light is again traveling between 2 points, but the speed at which the light travels is different in these 2 regions. The light travels faster in this top region and slower in the bottom region. Light really does travel at different speeds through different materials, like water, glass, plastic, and air. So try drawing the fastest path between these 2 points. See if you can get a time that's less than the goal time down here. Hey, great work! So yeah, here's a path that reaches the destination in under the goal time. This might be ever so slightly off from the fastest possible path, but you get the idea. So when light travels between materials with different speeds of light, like water, glass, and air, the light actually bends at the interface or border between the materials. That's how light takes the fastest path. It spends less time in the slower material. Now, is light actually figuring out the fastest path with some sort of intelligence? The answer is no, but we'll save that for a more advanced lesson. Next, let's see what happens if we flip which is the faster region and the slower region. So now the slower region is on top and the faster region is on the bottom. See if you can figure out the fastest path and beat the goal time. Now, the amount of bending in the fastest path depends on the speeds in the 2 regions. So here's an example where the fast region is really fast and the slow region is really slow. So there's a big change in speed once light crosses the interface. Let's try out the fastest path from before, which looked something like this. As you can see, that's slower than the goal time down here. Because this slow region is so slow, we really want to minimize how much time the light spends in it. We want to get out of the slow region as quickly as possible, going straight up. So in this case, the fastest path looks something like this, with a big bend. And sure enough, now we're under the goal time. And what happens if the speed of light is very similar in the 2 materials? Well, there's not as much of an advantage of having a big bend in the path like this. Perhaps a more direct path will get you there faster. Try beating the goal time now. Right, so when the speed doesn't change much from one material to another, light won't bend as much, taking a straighter path. And if the 2 regions have the same speed of light, then the light will take a perfectly straight path between them. Now, this notion that light bends when it passes between materials is called refraction. So this apparent bending of the pole is just one example. The refraction of light can be used to explain a lot of the things you see in the world around you. Ever look down in a pool? you'll see bright streaks, also known as caustics, due to the refraction of light by the waves at the surface. Refraction is also how lenses work, like the lenses found in glasses, binoculars, and telescopes. By bending light as it passes through glass, these lenses can focus and magnify faraway objects. Refraction also explains mirages, which look like reflections on a desert horizon. The light is actually bending as it passes between warmer air and cooler air. Refraction also explains how fiber optic cables work and how light is able to travel the entire length of the cable without leaking out the sides, only coming out of the tips. And as you'll see in a later lesson, refraction even explains where rainbows come from. And yes, it also explains where double rainbows come from. In this lesson, we'll explore where rainbows come from. So first, what do you notice about the rainbow in this picture? Well, it looks like a circular arc, with red on the outside and blue and violet on the inside. But there are other things to notice as well. The sky actually appears brighter inside the rainbow and darker outside, right? Also, there's a second rainbow over here that's a little dimmer. Let's see how much of this we can explain with refraction, the bending of light. So suppose you have air and water. Light actually travels faster in air and about 25% slower in water. So then how would a ray of light travel between points in the water and air? Would it take a straight path? Would it bend this way, spending more time in the water? Or would it travel this way, spending less time in the water? Right, so light bends or refracts between water and air, spending less time in the water. So how does this explain rainbows? Well, rainbows are formed by the refraction of light by raindrops, which are small spheres of water. When sunlight hits the raindrop, some of it reflects, bouncing off the water. The rest of the light refracts, bending as it enters the water. Then, once it reaches the water-air interface again, some light refracts again, bending out of the water, while the rest reflects, bouncing back through the raindrop. And the same thing happens again over here. Some light reflects, and the rest of the light refracts. It turns out that the light following this path, refracting into the water, reflecting off the back of the raindrop, and refracting back out, this is the light that causes rainbows. Let's explore this a little further with some interactive raindrops. So here you can try hitting a raindrop with different rays of red light. Notice that the angle at which the light comes out of the droplet depends on where the light hits it. See if you can determine the largest angle at which red light comes out of the raindrop. You can actually calculate this angle precisely with some trigonometry and calculus, but for now, just try using this interactive. What's the largest angle you can get? Exactly, so the largest angle at which red light comes out of a raindrop turns out to be about 42.5 degrees. Now in this next interactive, you can hit a raindrop with many, many rays of red light. For some rays, the angle is smaller, and for others, the angle is bigger. Here's a histogram, or graph, showing how often light comes out at different angles, from 0 degrees to 42.5 degrees, the largest angle. So try moving this yellow dot up and down, sweeping this raindrop with many rays of red light. After you do this a few times, what do you notice about this histogram? Precisely. If you sweep over the raindrop with many rays of light, you'll notice there's a peak in the graph. A lot of light comes out at larger angles, close to 42.5 degrees. So why is that? It's because light hitting the middle of the raindrop is spread out over a wide range of angles, while all the light near the ends of the raindrop comes out very close to the maximum angle, resulting in a peak in the graph. So the light coming out of the raindrop has an intense peak at the maximum angle, which for red light is 42.5 degrees. Okay, so there's a lot of red light coming out of the raindrop at 42.5 degrees. But what about the other colors? Well, different colors travel at slightly different speeds through water, so they actually bend different amounts when entering and leaving the raindrop. So in this interactive, you can actually see the slight separation of all the colors. Here, we've labeled the angle at which green light comes out of the raindrop. So what's the largest angle for green light? Exactly. The largest angle at which green light leaves the raindrop is about 41.5 degrees. Finally, let's look at the end of the spectrum, violet light, whose angle we've now labeled. So what's the largest angle at which violet light leaves the raindrop? Okay, so you found that the largest angle at which violet light comes out of the raindrop is about 40.5 degrees. Alright, let's put everything together to explain rainbows. Earlier, you found that a lot of red light comes out of the raindrop at the maximum angle of 42.5 degrees. And the same thing happens for all the other colors, except each color has a different maximum angle because of how they bend in the water. Violet light peaks at the smallest angle, 40.5 degrees. So between 40.5 and 42.5 degrees, we have peaks of all the different colors. So suppose you're looking at the rain, and there's sunlight coming in from behind you. If you look in a direction that makes a 42.5 degree angle with the sunlight, then intense red light is coming out of the raindrops in your direction. And if you were to look a little lower in the sky, in a direction that makes a 40.5 degree angle with the sunlight, then the raindrops are sending violet light in your direction. And for all the angles between 42.5 and 40.5, each color has a peak intensity. And you'll see these colors in any direction making these angles with the sunlight. The result is a circle in the sky, a rainbow. A good chunk of the circle is actually below the horizon, so you wind up seeing a circular arc. And remember we noticed that the sky was brighter underneath the rainbow and darker over the rainbow? Why is that? Well, here's our graph of the different colors coming out of the raindrop. Notice that for angles greater than 42.5 degrees, there's no light of any color coming from the raindrops. So these angles will appear to be darker. And for angles less than 40.5 degrees, all the colors are coming from the raindrops in approximately equal amounts, with less intensity than the peaks over here. So this will be a brighter region. And that's exactly what we see. Smaller angles under the rainbow are brighter, while larger angles over the rainbow appear darker. Okay, one last thing. What causes the double rainbow, this secondary rainbow out here? Well, remember the rainbow is explained by this light that refracts into the raindrop, reflects, and then refracts out of the raindrop. But if we analyzed the light that reflects a second time inside the raindrop, we'd get more light refracting out up here. This is the light that causes the second rainbow. After all these reflections and refractions, there's less light that winds up following this path. And that's why the second rainbow is less intense than the primary one. So there you have it. Not only have you discovered how rainbows form, but you've explored quite a few interesting properties of rainbows along the way. Nicely done.